Okay, so this is going to be our final section of 1345. We're going to talk about power generation and power distribution. So the way this is going to go is we're going to start talking about DC power. Now, I'm going to go over all the specifics. We'll link in the description to the video in general. We talked about all the specifics about how power gets generated. But we're talking about on a bigger scale of what does it look like on an aircraft and how does it get distributed and what do those systems look like. Once we get done with DC, we're going to go into AC. Then we're talking about like constant speed drives and IDGs. Then from there, we'll talk about starter generators and all the nuances that come with it. And then finally, as a wrap up, we're going to look at the 737 MAX's power distribution system and talk through all the details of what that system looks like and why does it work the way that it does.
Okay, so just as a reminder, we're going to talk about how a generator works. The principles of electromagnetic induction are that the voltage is induced in an armature of a generator throughout the entire 360 degree of rotation of the conductor. The armature is the rotating portion of the DC generator, and as shown on this graphic right here, the voltage being induced is AC. All right. Since the conductor loop is constantly rotating, some means must be provided to connect this loop of wire to the electrical load, as shown in the bottom right-hand graphic. Uh, uh, Slip rings and brushes can be used to transfer the electrical energy from the rotating loop to the stationary aircraft loads. All right, so that's a fancy way in the 8083 to say that as that armature loop passes by the north and south magnets right there, what you get is a cycle, and you can see it up on the top left-hand corner of positive and negative voltage. That's alternating current. It alternates, positive, negative, goes up and down. At that, those electrons flow down the armature into to the brushes. Now the brushes are being depicted there. Those little black blocks snug up to the commutator right there, and then they're connected with a resistor. It basically means that it goes to a load. In this case, it's going to be everything on the airplane. But that's basically how a generator operates.
Okay, here we have a generator that's off of an aircraft that we're going to show you what it looks like in real life, not just a graphic. Here are going to be your coils, your magnet. Here's the commutator. This is the armature. So you think that those loops that you see on there, this is the outside of them. And as it spins, you can see that it has like opposing sides to each one. Notice how close it gets. And that's what that's doing is as these generate an electromagnetic field, these guys right here are spinning by and they're grabbing electrons. Imagine like this is like a fish net, and this is like a coral reef, and all the fishes are swimming around the coral reef. And as the net comes by, it grabs those electrons, and it comes down. It's electrically moved down to the brushes. Now this is what a brush looks like. Let's see if we can pull it out here. You notice that they're flat. All right. That's something that you'll do. You'll do a brush inspection on starter generators and things like that. And what you're looking for is these wear marks. Now, this spring pushes down on the brush and make sure that it's in contact with the commutator right there as it's pumping the electrons out. Those electrons will come through the brush, through this wire, and out into the rest of the airplane. But in order to do this, in order to make sure that you have that contact, you have to have some sort of sacrificial layer that will wear off as time goes on. That's what this is right here. And so you have to inspect the brushes to see where they're out in the wear marks, and then if they are wore out, then you have to turn around and you remove the brush. And that's a brush inspection. It's pretty standard. But that's the basics of how a generator will operate.
All right, so this graphic kind of gives you an idea of the position of your armature and how it inducts the electromagnetic force into the system. And so, like you notice that as the armature spins, the flow of electrons changes. All right, so the big problem that you end up having is you can't have power just pulse up and down, up and down, up and down, up and down as it goes. So the question becomes like, how do we make the power more stable and with less variance? And how do we make the question becomes like how do we make multi-phase power, and then we just simply just add armatures to the already existing generator. So instead of having just one, we end up having multiple arms of the armature. So that way, if you look on the bottom of this graphic right here, you'll see that the peaks are much more frequent, and then the troughs are very slight, and that gives the illusion of a steady state, stable power. But technically, what's happening is that like as one induction comes to its peak and then starts to fall off, the other one is right behind it, creating a peak. Okay, so let's just look through this graphic out of the 8083 and make sure that we fully understand all the kind of the parts and pieces of a generator, because we're going to end up working on them here in just a little bit. All right, so we're going to start in the top graphic, and we're just going to work our way clockwise. All right, so you have the connector lugs. That's just all that is like the generator has to have a place to take the power that it's gathered from its operation and pipe it into the rest of the airplane. So if you think of the generator as kind of like your water plant or whatever that's like getting water from a lake, the water plant itself has a main, and that main comes out to the rest of the town, and then the town just grabs off of that water main as time goes on. The field frame is literally just a frame; it just holds everything together. Then you have the drive-in frame and the sealed bearings. Those are all just parts and pieces of the infrastructure of the generator. The drive shaft is where this generator will eventually marry up to something else, some other sort of thing that will turn it. So you don't get power for free unless Nikola Tesla gets resurrected and starts coming up with new and interesting things that we don't know about yet. So you have to get power from somewhere. Well, the way that we get power, at least in this day and time, is to burn fossil fuels. So or not, or any sort of fuel really. And so what this typically will look like is that you'll have a battery that will turn a starter that will then suck in like air mixed with fossil fuels, and then it'll light off into a big explosion, and that explosion that goes over turbines or uses a piston to turn a drive shaft. That drive shaft then turns gears. Those gears are then married up to other devices with gears in them, to in this case a generator, which then turns as those primary gears turn, the drive shaft gear starts to turn, and that turns your armature, which then produces your electrical power. So the drive shaft is really important, and we'll talk more about that on the hangar floor as y'all take things on and off. Then you have the field winding. That's going to be what actually gathers the electrons. A screw. I guess you have to have screws to hold things together, right? Pole shoe. That's just another part of the field winding infrastructure that kind of holds it all together. And you have brush and brush holders. We just looked at what the brush does, and you have to have those little springs to hold it and keep that tension correct on there. Steel ring is just more infrastructure parts of it. And the commutator is where the electrons then start to get piped into to the rest of the system itself. Then you have your brush connector bars. That's pretty self-explanatory. And then on this case, this one has an air scoop. So the air scoop is basically there to cool it. You can imagine like the amount of friction and the amount of just electrical energy that's being transmitted and generated throughout this whole operation. Anytime you have any sort of energy changing hands or moving, heat's always a byproduct. If you remember kind of your 10th grade chemistry class, as that heat gets produced, then you can't just sit there, or else we'll literally burn generators up if you start having like those brush dust, kind of like brake pad dust, very similar type of construction. If it clogs up the airflow, then the generator will get too hot, and then the generator will fail because of it. If we look at the bottom part of the graphic, this is just another idea of like what the field frame looks like. We looked at that in the generator out in the avionics room. You have the commutator end frame. It's another piece of infrastructure for it. The armature itself is kind of really the biggest moving part of the whole thing, and then the drive end is just it goes out to where the output shaft is, or where the drive shaft's at, so that actually help it turn. But that's basically kind of the the bee's knees of generators. That's like all of the parts and pieces that you need to know to understand how a generator works. They're really not that complicated. They're fairly simple devices when you look at them, and they've been around since the late 1800s, so nothing too complicated being generated then. All right, this is a picture out of the 8083 of a field frame. It's a much smaller generator than the one that we were looking at, but that kind of gives you an idea. You can see the brushes there on the back that are hanging off, attached to their holders, and then the armature will just slide into this, and the gap between the armature and the field frame is going to be very small. If you think about it like on a lawnmower, the coil gap, which is a very similar type of construction, is a dollar bill that's been folded over twice. It's like a little old man knowledge for you. All right, and then this is an armature. It's a drum type, so it's a little bit different than most, but it has all the same parts and pieces. You notice the coils are in. There's a drive shaft that comes out on the far right hand side, and then the commutator that is the part that where the electrons are going to flow from the armature itself as it passes by the magnets, and then it'll come out. All those electrons will pile up on the commutator and then get grabbed by the brushes as and then inducted into the rest of the generator system. Okay, so there's three different types of generators out there in terms of the way that they are wired. This is the first one, a series wound DC generator. Now, this is the simplest, but it also has very poor voltage regulation because it changes too much. So therefore, you'll never see this on aircraft. But if they ever talk about a series wound DC generator, that's what they're talking about. This is what it looks like. All right, so this is a field or a parallel wound DC generator or a shunt wound DC generator. They basically mean the same thing. Now, the big addition here is the field rheostat that you see on there. Other than that, it's very similar to the series wound DC generator. Now, typically on an aircraft, they're going to take the field rheostat off and they're going to put a voltage regulator on there, and which we'll get to towards the end of this class, what a voltage regulator is and does and what they look like. Okay, so the most complicated one, and therefore the most common one, is going to be the compound wound generator. Now, there's a lot happening here, but the big takeaway is that you have both series and parallel advantages that are being leveraged to produce the most stable current that can possibly be produced by a DC generator. So there's your three types. You have your series, your parallel, and then your compound wound generators. Okay, so what kind of maintenance can we expect on a DC generator? Well, we've already talked a little bit about this, about the brushes. Now, the 8083 is going to outline a procedure to use sandpaper to help seat the brush. I'm going to tell you, I've done a lot of this type of work, and I've never actually seen the sandpaper be employed. But there's not saying that you couldn't, going off of the component manual or the aircraft maintenance manual, they may call for you to seat a brush this way. Most of the time, what ends up happening is you're going to look at those wear marks, and you're going to turn around and just exchange the brushes as needed. Now, I would encourage you, just kind of as a good practice, if you exchange one, just go ahead and do them all, so that way they're all kind of like on the same path. Sometimes you'll get a generator where somebody just did one, and then what that ends up doing is that like you'll basically always be replacing one brush on it. Whereas a lot of times if you just replace them all, make them all level set, all the same, then you won't have to worry about that. You won't have to worry about brushes, but like every fourth or fifth inspection, because it takes time for these things to wear down. But brushes by far are going to be your biggest maintenance item on a starter generator, DC generator. Okay, other parts and pieces of maintenance that you're going to be looking at whenever you're inspecting a DC generator, you're always going to be doing GVIs, a general visual inspection of different areas. You're looking for wear, you're looking for any sort of looseness that shouldn't happen. So you're going to grab the drive shaft, and if it starts moving all around, there's going to be something not right there. There's going to be a bearing going out. And these things, they move, and they wear and tear, and it's subject to heat and dirt and things like that. So they will fail from time to time. So you always want to make sure that it is also secure. That like whenever you pull it off, that it actually is secure on the accessory gearbox mounting or engine, however it's mounted. Grab it before you start working on it. Just kind of give it a little shake and see if there's any play. Any play could actually be a pretty significant ordeal for these DC generators. You also want to look at like the electrical connections, make sure they're not frayed, they're not corroded, they don't just break off in your hand whenever you come off. And that's most of the time. Like you're going to have either one or two power leads that go to it. Sometimes, depending on the model, you might have one lead that comes off of every phase. You want to make sure that every single one of those doesn't show any sort of sign of corrosion, any sort of sign of breaks or cracks, or anything that's going to cause the generator to fail, or even more so if the wire is starting to break internally and it's basically shortening. That means that it's going to get hot, and that could potentially lead to a fire. So you always want to check that kind of thing. Make sure that it's clean. Like I said earlier, the brushes are effectively like little brake pads, and so they're going to have like brake dust that produces it. And so you'll see that kind of fine brake dust all throughout the generator. It's not that big of a deal, but what you don't want to do is it start to pile up in one area and start blocking airflow. So if you're taking these apart and you have access to shop air, definitely blow them out. Get all that dirt and grit and grime, and then just pay attention to the component maintenance manual and the aircraft maintenance manual, because it will tell you other little areas to pay attention to. Whenever you reinstall it, you're always going to want to do a maintenance operational check or MOC. You're going to hear me start using that a lot more. And make sure that you're getting the power that you need, like from the cockpit standpoint. Go up there and check it, and we're going to go over the Max's DC power panel, so that way you can know what right looks like there. But also go back to the generator itself as the engine's running and it's moving, and just listen to it. If it sounds like there's something not right, then there's something not right, and you need to address that. If you notice any sort of movement or any sort of like sparking or weirdness, then shut down and start trying to investigate what's going on there. I will tell you, a lot of that's like really uncommon. These are pretty simple devices, and they're pretty reliable. Outside of a little bit of a brush maintenance and blowing them out with air and stuff like that, just kind of general maintenance that you would do on just about anything. There's not a whole lot to worry about with DC gens.
All right, so now that we've talked about power generation and distribution, let's talk about power regulation, voltage regulation, overcurrent, over voltage, under voltage, and what devices do we have that are baked into the system that will prevent damage from those types of conditions.
Okay, so a voltage regulator does exactly that. It just regulates voltage. Now, aircraft are meant to run on very specific voltages. Most of them are like 24 volts or 28 volts, so on and so forth. Just depending on the type of aircraft that we're dealing with. Is it a heavy commercial airplane? It's going to have a 28 volt DC system. If it's smaller ones, maybe it's 24, maybe it's even 12. And so the main thing is that there is a set voltage for all the devices on the aircraft to operate with. And if it gets more voltage than what it wants, or less voltage than what it wants, then things don't operate properly and damage could occur. So an aircraft generator output can easily be adjusted, though, through the control of the generator's magnetic field. The strength of the magnetic field has a direct effect on the generator output. So stronger the field, stronger the output. Weaker the field, the weaker the output. It's pretty simple. So more field current means more generator output, and vice versa. So the graphic that we're looking at right now shows a simple generator control that's used to adjust field current. When the field current is controlled, the generator output is also controlled. And keep in mind, this system is manually adjusted and would not be suitable for aircraft. It's just there for demonstration. Aircraft systems have to be automatic, and therefore they have to be a little bit more complex. So let's look at some of those. Okay, so the first type of voltage regulator is going to be electromechanical. It's a fancy way to say like relays and things like that. These are generally found on older airplanes. They are not. You generally won't see them on on a modern aircraft, especially not on heavy commercial airplanes. So we're not going to spend a whole lot of time on that. Just know that you can do it through you can regulate voltage through an electromechanical means. Okay, so this is a solid state device, often called a generator control unit or a GCU. Now, I'm going to use GCUs probably for the rest of the time because this is the most common way to refer to them. But effectively, they're kind of like little computers that essentially say, like, hey, look, is the voltage correct, and what do we need to make adjustments to anything to get that voltage to be correct, because the job of the generator is to supply a stable voltage at a certain voltage to the aircraft at all times. If it's not doing that, it's going to cause multiple failures and problems, and probably create fires or under voltage problems, things like that. And so the GCU is actually a really important piece of equipment to be tied to the side of the generator. Okay, so what does a GCU actually do? So here's a GCU on a 3.7, and we're just going to kind of go over the things that a GCU does. First off is the over voltage protection feature. So the over voltage protection system compares the sampled voltage to a reference voltage, so it knows what it's supposed to do versus what it's actually doing. And the over voltage protection circuit is used to open a relay that controls the field excitation current. Typically, it's found on a little bit more complex GCUs. The most modern aircraft are multi-engine, and a GCU basically helps run or helps coordinate the parallel generator operations. So a paralleling feature has to be employed to ensure that every generator that's in the system is operating within limits. So in general, paralleling systems compare the voltages between the two or more generators and adjust the voltage regulation unit accordingly. So that way everybody is on the same page, and you don't have like one generator that's overproducing or another one that's underproducing, or so on and so forth. Okay, overexcitation protection. This is actually a really interesting one. So when you have multiple generators that are working to make everything go all copacetically, and you have one of them that fails, then all of a sudden another GCU could say, like, hey, look, our power's fallen off. Now we need to increase the power to compensate for what's been lost. And effectively, you could have like one generator doing the job of two generators. Well, that one generator is not really built for that. Just like with people, if you have like one guy on a team that's like overworking to compensate for other people not doing their job, that guy will burn out. Well, a generator will burn out. It'll catch on fire and do any number of things. So if you have one generator that basically just quits for whatever reason, just a hard failure, and then you don't have overexcitation protection that's built into your overall architecture, then that second generator is going to simply just start producing more and more power, and eventually it'll just burn up and cause a fire. So what it looks like is that generator number 2 failed, but what actually happened is generator number 1 failed and then caused a ripple effect on generator number 2. So overexcitation protection is something to note and be aware of. Okay, so differential voltage is another really interesting one. What will happen is the GCU will look and see, like, hey, look, what's the voltage inside of the system right now? And it should be about the voltage that generator wants to produce. Well, then it looks at the voltage that is actually coming off of the generator and says, like, hey, look, are these two voltages within a certain tolerance, or a really, really tight tolerance? Basically, are they the same? And if they are, then it closes the tiebreaker, and boom, off it goes. But if it's not, then it won't let the tiebreaker actually close and connect it to the rest of the system. Okay, so the last one that we want to talk about is reverse current sensing. Now, this is a little bit more complicated, but it's not too bad. If you think about it, all a generator is a electrical device. Now, if that electrical device has a positive electrical pressure, then current will flow out of that device and into the negative pressure area, right? Think about it, like if you were to have two tubs of water that were connected, but also you put a lot of pressure on the on one tub of water, it would push water out of that tub and into the other tub that's not pressurized. The electricity is basically the same thing. So if the generator is producing a lot of electricity, then the electricity is going to want to flow out of the generator and into wherever the load's at, wherever like the low pressure area is. But if all of a sudden, like the generator starts to fail, and then starts to draw electricity back into it, then and like the other generators are doing just fine, they're all tied together. Also, the other generators are producing more electrical pressure than that generator. Then that generator effectively becomes a load, and the current will reverse. And what you don't want to have happen is that, because you don't want to just have this drag on the system as you're flying around. All of a sudden, that generator starts to fail, and now not only is it not producing the power that you need, now it's costing you the power that the other ones that your safety systems are trying to supply you. So that's one of the things the GCU does, is it looks at that situation and says like, hey, look, the current's going the wrong way. We need to isolate this generator before it takes the whole system down. All right, so let's talk about a couple of these voltage regulation devices. First is the carbon pile regulator. So carbon pile regulators control DC generator output by sending the field current through a stack of carbon discs, which you can kind of clearly see there. There's little black discs that are being held on by springs. The carbon discs are in series with the generator field, and if the resistance of the disc increases, the field current decreases and the generator output goes down. If the resistance of the disc decreases, the field current increases and then the generator output goes up. So it's kind of a natural regulatory device for that. So that's a carbon pile. All right, the carbon pile, while it's kind of cool that it naturally wants to regulate voltage, has actually been largely pretty much replaced. You don't really see those anymore. Kind of the next one up in sophistication will be the 3-unit regulator. That's kind of a picture of the one that we saw earlier. You have 3 relays that react as needed to the detected situation, and they open and close the relays to help manage the level of voltage or to regulate the voltage would be the better way to say it. Okay, so current limiters are something that you'll get really familiar with because they are actually on the Lear. There's a lot of them on the Lear because that was what was kind of the state of the art whenever the Lear was produced. However, on modern aircraft, they are slowly but surely being replaced, if not outright just gone. Okay, earlier we talked about reverse current sensing. Here's a reverse current relay. Most of these, where they're employed, have been like integrated into GCU, so you generally won't see them, but you could, especially if you're working on older aircraft, depending on where you go, because aviation's a wide world. But essentially, all these really do is detect that the current's going the wrong way, and it opens the circuit so that way it can't flow it can't flow back into the generator or into some place where they don't want. This sort of methodology, even on 737s, is pretty common to be able to reverse current simply by opening and closing relays. So that's something that you do want to get used to dealing with, and troubleshooting relays is a pretty viable skill for you.
All right, it doesn't make a lot of sense for an aircraft to have a starter, which is effectively a DC motor, and then a generator, which just generates DC power. It would make a lot of sense if you could put those together and make one unit out of 2 different units. You would save weight, you'd save the complexity of it all, and you would be able to do a lot more with just one thing. Therein lies the beauty and the brilliance of a starter generator. Now, starter generators are pretty well ubiquitous across all turbine engines. Some of them don't have them. Some of them you might use something a little bit different. But I guarantee you, if you're going to be working on, especially in like the business, corporate aviation world, starter generators are par for the course. I know for a fact if you end up working on like a Bell 206, 407, they have a starter generator that's about like so big, and you'll end up having to change the brushes and all the other good stuff.
All right, so this is the kind of run-of-the-mill starter generator you'll see on a lot of small turbo shaft, turboprops. This one's specifically is off a Rolls-Royce turbo shaft engine. You'll notice that it looks a lot like a DC motor, a DC generator. It's the same thing. It's not really a whole lot to see. A couple of things to point out. If you'll look, the drive spline there is covered up so that way it doesn't get knackered in the process of moving it. But if you take a step back and you look at the grate that's on the front, that's to help open up airflow. If you ever have any dirt or anything, that's basically where it's going to be at. You can't see it on this photo, but on the back side, the flat side on the right hand side of the image, that is also a big open grate to allow air to just flow through there as needed. Notice the top, that terminal block that goes all the way around. There's several terminals that will go onto this aircraft, and the reason being is that not only is there a circuitry for going direct to the battery to chart or to spin the motor to spin the engine up to get started, but there's also another pathway to go to the battery charger and then into the battery and indeed to the rest of the aircraft system. And that's where it sits on the Allison slash Rolls Royce turbine engine. If you look in the center of the engine, at the very bottom, there's a big gray square looking thing that actually is the starter generator, and it just mounts right up to the accessory gearbox of the engine, which you'll understand more when we get into turbine engines and stuff. But notice that it just plugs right up, and it's always connected. It's always turning. The real question is how is the electricity flowing through it? Is it being generated and flowing out of it, or are we taking a battery and are we charging it? So that way it'll action and start the engine.
All right, now that we have a handle on DC power distribution, let's see how much or how little AC changes that.
All right, so most aircraft use DC power, and if they need something in AC, they'll just use an inverter, and that we'll get to here in a minute what an inverter is. But they'll use an inverter to produce that AC power. However, on large aircraft that use a lot of power, they'll actually employ AC alternators. So virtually all transport category aircraft, like the 757, 767, 777, Airbus A380, they all employ at least one AC alternator driven by each engine. Now, these aircraft also have auxiliary AC alternator driven by the auxiliary power units. The APU will also have their own. In most cases, the transport category aircraft also have at least one or more AC backup power source, such as a AC inverter or a small AC alternator driven by a ram air turbine or the RAT that you see pictured here on your screen. Now, during an emergency, this will deploy and it'll start to spin because it's basically a little wind turbine, and that produces AC power that will drive some of your key systems to maintain life, maintain flight. Now, as a maintainer, you'll always end up having to test this. There's rat checks that end up having to happen. And I'll tell you, and the maintenance manual in your company, whoever you're working for, should also make this very clear to you. Stay clear of that thing, because when it comes down in a hurry. And I've watched guys get smacked by it because they were walking underneath the aircraft whenever there was a rat check that was going to end up being happening, and it doesn't turn out very well for them. Now, what makes an alternator different is that it actually produces 3 voltages every time the armature goes around. And those voltages are going to be separated by 120 degrees of their peak sine wave. So every time that armature moves, it's grabbing 3 different types of voltages, and it's pumping it into the system. And that allows for this very stable power source, and also a large amount of energy as well. Now, another kind of key distinguishing feature with these big alternators are that they don't use brushes. They actually use brushless magnetic pickups to grab the electrical energy that's being generated and move it into the wire. You'll hear them called brushless AC motors or brushless motors. Really big in like if you get into the RC world with like little T-Rex helicopters, they'll always talk about like these brushless AC motors that they have. But they're also employed on heavy commercial aircraft as well. Those magnetic pickups that grab the electricity are really useful, and it drastically improves the life of the alternator, simply because you don't have a consumable part that's in there. So that means that there's less maintenance. That means that there's less debris that's entering into the windings and all the bearings and everything that moves inside of that alternator. So it prolongs its life almost indefinitely. Okay, so how does this actually work? Now you can look at this graphic and you can see that there's actually three generators. There's the exciter generator, the pilot exciter generator, and the main AC generator. That's the typical armature winding and field windings. And the need for brushes is eliminated by using a combination of these three distinct systems. The exciter is a small AC generator with a stationary field made with a permanent magnet and two electromagnets. The exciter armature is three phase and is mounted on the rotor shaft. The exciter armature output is rectified and sent to the pilot exciter field and the main generator field. Now, the pilot exciter field is mounted on the rotor shaft and is connected in series with the main generator field. The pilot exciter armature is mounted on the stationary part of the assembly. The AC output of the pilot exciter armature is supplied to the generator control circuitry, and where it's rectified, regulated, and then sent to the exciter field windings. The current is sent to the exciter field, provided the voltage regulation for the main AC alternator. And if the greater AC alternator output is needed, there is more current sent to the exciter field, and vice versa. Now, in short, the exciter permanent magnet on an armature starts the generation process, and the output of the exciter armature is rectified and sent to the pilot exciter field. The pilot exciter field creates a magnetic field and induces power in the pilot exciter armature through the electromagnetic induction. So effectively, it creates a magnetic field and that just attracts all of the electrons into the system, as opposed to actually creating a direct pathway for them. Now, the output of the pilot exciter armature is sent to the main alternator control unit and then back off into the exciter field. As the rotor continues to turn, the main AC alternator field generates power into the main AC alternator armature, and also using electromagnetic induction. The output of the main AC armature is a three-phase AC and uses to power various electrical loads.
Okay, so lastly, let's talk about inverters. Now, like you might be able to generate power in one way, but maybe you need it to be inverted and change the power to a different type of power going somewhere else to run a different sort of application. Or maybe you want to have the redundancy to be able to go from AC to DC, DC to AC, so on and so forth, just so that way you're that much more safe as you're flying around. Let's talk about
All right, so we're not going to get too far into the details about how a inverter works, but effectively this is it. We're going to use different transistors to effectively open and close different gates to help produce a nice smooth wave. Well, a ripple effect, and then the capacitors get employed to actually smooth it all out. So we have this nice solid power band that comes off of it. Just know that it is an inverter is using comparators, capacitors, and transistors all to make it work. Now, what we do want you to be able to do is be able to recognize them, what they do, and what they're for. Here is a DC to AC inverter off of aircraft spruce. It would be employed in a small general aviation airplane. The more that we see panels coming into work inside of aircraft systems, the more high quality power we need to run those types of computers and displays and so on and so forth. Because you think about how much information it's processing, how fast. In order to have that high quality power, you're going to have AC power, and the AC power, the easiest way to accomplish that is simply by inverting the DC power that the engine's already producing. And so you'll see these types of systems far and wide, and especially more and more as the future goes on. Now, when you get to the 737s, your bigger heavy commercial aircraft, this is what they look like. They're huge. There's actually an airworthiness directive that went out not too long ago about these overheating. They're just getting older, they get dust in them, so on and so forth, and then they get hot and they'll burn up, and they could potentially cause a fire. But that's what that's what an inverter looks like. They'll call this a static inverter on a heavy commercial aircraft.
All right, let's talk about constant speed drives, or CSDs, or integrated drive generators, or IDGs. What's their role, and what do they look like in this power distribution system?
Okay, so one of the challenges with aircraft power generation is that it needs to be a very high quality, and it needs to be very very constant. So aircraft AC current needs to be generated and maintained at 400 hertz AC. All right, now that becomes very very difficult whenever you're using a an alternator or a DC generator that's being taken care of by tying that into the engine. Reason being is pretty simple. Like the engine doesn't necessarily stay at a constant RPM all the time. It'll go up, it'll go down. You think about whenever you're taking off, you firewall the engine, it goes up, but then you're gonna pull it back to a cruise power setting. And even more so if you're talking about like helicopters or maybe an aircraft that like a fighter plane or an air show demonstrator or something that has to constantly make throttle inputs on a regular basis. Now that means that since it's not going to produce a constant RPM, it's really hard to produce a generator or an alternator that will produce the right frequency of electricity at the right voltage constantly. And so they've come up with a system that will do that for us, and it's called a constant speed drive or an IDG. Now, all AC alternators, they have to rotate at a very specific RPM to keep that frequency of the AC voltage within the limits that the airplane can tolerate, which is not very much. They're pretty tight. So aircraft AC alternators should always produce a frequency of approximately 400 hertz. If the frequency strays more than 10% from the value, the electrical systems don't operate correctly. You get all kinds of erroneous problems that you, as a troubleshooter, you're going to turn around and start chasing your tail, because what the problem that you're chasing is actually not the way the symptom that's manifesting. Like if it's showing you that you have like low fuel or something like that. It's actually just the quality of power that is that's being generated. So the constant speed drive, or a CSD, is used to ensure the alternator rotates at a correct speed to ensure a 400 hertz frequency. Now, the CSD can be an independent unit, or it can be mounted within the alternator housing. And when the CSD and the alternator are contained in the same unit, the assembly is known as the integrated drive generator, or the IDG. Now, the CSD is a hydraulic unit similar to in an automatic transmission found in a modern automobile. The engine of the automobile can change RPM while the speed of the car remains constant. This is the same process that occurs for an aircraft AC alternator. If the aircraft engine changes speed, the alternator remains constant. A typical hydraulic type drive can accomplish this just in the same way that a propeller governor keeps the propeller RPM the same speed, or the car keeps the car's speed constant despite lower power input. So you think about let's run with the metaphor of the transmission in the car. As the power system goes up, and you want to get the car's not moving, so you want to try to maximize that power that the engine is producing as much as you possibly can to have the highest possible torque to move the car forward, so you're in first gear. But once you've got the car kind of rolling, then all of a sudden first gear really kind of becomes a drag. It kind of limits you, so you go to the second gear. Now that's optimized for that speed and that power setting. But then, like, as you really start to kind of get going, you're like, we really need to be kind of cruising. We don't need this much power, so you go to third gear. That allows you to have a lever to leverage the amount of power the engine is producing, which is like lowered now significantly from whenever it first took off, but still maintain the speed that the car has been moving. And then it keeps on going up and up, fourth, fifth, sixth gear, and that allows you to economize the engine as much as possible. That you don't need to be 7,000 RPMs to be going 70 miles an hour. You might be able to only do 1,900 RPMs and maintain 70,000 hours. But of course, if like you come to a stop and you have to do the whole process again, you need to be able to go down, grab a smaller or a lower gear to trade that high speed, high performance for more torque, and vice versa. There's not really that much different that's going on right here. We need to make sure that the engine or that the the alternator is producing 400 hertz AC. We know that the alternator will produce 400 hertz AC if it spins at a very certain RPM. So the gearing inside of the IDG or the CSD basically ensures that whatever the power setting, as long as the engine is running, we're going to spin the alternator at the right power setting to produce those 400 hertz AC, high quality, high grade power for the electronics that we're going to be taking care of.
Okay, here we have a JT9. This is used on 747, and the 747 has a lot of electronics. Right here, you'll notice the CSD. It'll be the constant speed AC generator. Notice that it looks a lot like, I mean, it's the transmission, but so like it looks a lot like a helicopter transmission or something that has a sight glass that needs to be filled and serviced on a regular basis. So that's something that you, if you're doing pre-flight or you're returning an aircraft to service, something that you'll have to take care of on a regular basis. But that is what a real-life CSD looks like.
Okay, so let's look at the 737 MAX and just see what its power distribution system looks like. So this is kind of like an overview of the whole thing to include locations. And these are all the different spots, or all the different components, rather, that power can enter into a 737 MAX. Now we're going to start on the right next. We're going to work our way around. So we have the APU starter generator. Now, that's generally speaking, the APU has its own battery, and like you can turn you can get the APU going to generate power for the rest of the airplane, both air and electrical power as needed. So that's one way that you can power a 737 MAX. Then you have the IDG that is on both engines. So there's two different generators, and we're going to get into that here in just a little bit. That is tied to both of the LEAP engines that are tied there. Now in the eBay is where you get these four boxes. The static inverter, we already talked about that. The battery charger also is available there to charge the battery. So if you use the battery to start the engine, start the APU or whatever, that's going to draw down the battery. You need to have a way to put that power back so you can start it again. That's largely going to come from the battery charger. The battery charger is tied into the IDGs and that whole power distribution system, which we're going to look at here in just a second, and it'll go back in the battery that way. Then we have the TRU. It's a transformer rectifier unit. Is there. You can also rectify power as needed. Then the SPCU is a power control unit. We'll get into here in a little bit, but not necessarily a source of power, just a control device. And then you have the external power cart, so you can always plug up power from the ground. Okay, so not a whole lot to see here. It's the P19 panel on the 737. It will allow you to plug up power and do a couple of other things. So you can call the cockpit and you can talk to them with if you have like a David Clark headset up there. But it's that's where you attach the ground power. Ground power is generally pretty easy. The harder parts actually usually work in the GPU that you're plugging up to it. But let's say you plug up to it and the GPU is running, everything's fine. When you go up in the cockpit, you'll see on the power panel that we're about to look at, it'll say ground power available, and you press that button, all lights and stuff comes on, and you can start turning things on from there. But that's a pretty common way, especially for maintenance. Ground power is kind of like your typical way that you're going to power the aircraft. You don't want to leave them on batteries or anything else like that. But if you had like a dead battery, you could, in theory, plug up to the GPU, turn power on, and then get the batteries charging that way. That's fairly common practice out there. Okay, you as a maintainer, troubleshooter, technician, you're going to end up looking at this panel a lot. It's the P5 panel that has all your power information on it. Now we're just going to we're going to concentrate on the actual panel itself. We're going to work our way kind of clockwise. So when you see bat discharge on there, that's a light that lets you know, hey, look, the battery is being discharged. It's showing power that's going out, and that means that you're working on a finite amount of time. If you have a bat discharge light on, that means that battery is going to die, and that probably means that the plane's already on battery power. But maybe it's not. TR unit, so it's an indicator to let you know that the TR light comes on when one or more of the TR units has a failure to ground. But it also comes on whenever TRU1, TR2, and 3 have a failure in the air. So it's basically saying like, hey, look, the TRU is failing. The electric light shows that there's a fault in the DC or standby power system, so that light will come on as well. If you go down below that rotary knob on the left is how you select what power system is going to be displayed on the display right there. Now notice you have like DC amps, DC volts, AC amps, AC volts, and CPS frequency. Now basically what that will allow you to do is do your first bit of troubleshooting. Now you can tell an old technician from a young technician, because the young technician is going to kind of do a lot of these things that aren't so obvious. They're gonna say like, oh, well, we have this failure, therefore it has to be this per the FIM or per this wiring diagram or whatever. The old guys a lot of times will sit down in here, and the first thing they do is they'll start flipping through and trying to see like what's our power at. And so like that means that they know that hey, look, our batteries system should be driving this type of power. Our standby power system should be driving this type of power. TRU 1, 2, 3, whatever. Like it should all show this type of power, because they know that some of these systems will throw faults if they're underpowered or overpowered or there's some kind of problem. So it's a really good thing to do is to start, playing, with that system right then and there. Right below that, you have, say like bat on and off. So like, that's how you turn your batteries on, turn your batteries off. So like if you have a plane that's on the ground, there's no GPU around, you need to check something, you have a limited amount of time that you can actually use the battery power. And as long as you don't go too crazy with it, it will it'll you have time to play with that battery, and it'll recharge afterwards. You have the IFE slash passenger seat power. You can turn the IFE power on and off. That gets lumped onto the P5, but it's not necessarily relevant to what we're talking about today. But IFE stands for in-flight entertainment. You can also check your indication of all your AC generating systems on that second knob to the right by going standby power, ground power, Gen 1, Gen 2, APU generator, the inverter, and then there's also a test. Now, the reason why those two knobs are really important for you to understand is that, like, if you have you're selected bat 1, bat 2, you're going to see nothing on the AC side of things, as opposed to if you are on like ground power or Gen 1, Gen 2, you're going to see like AC power coming off, but you might not see DC power coming off. Or if you saw your AC voltage was down or high, or your frequency is also like anything other than 400, these are all indicators that there's something wrong with the power generation system, and you're going to get these downfall, or these kind of like downstream effects on your other systems. So you might be getting all kinds of like maintenance messages that are popping up in the display system, but really what's happened is that your power system is gone. You've had a battery fail, you've had a generator fail, or something like that. So the P5 is always just a good thing to keep an eye on, and it's also a good thing to troubleshoot, because your power is your life on the airplane. If it's somehow messed up, well, then everything else is going to be messed up right behind it. So always remember to check the P5. Okay, so this is like a continuation of the P5 panel. If you'll notice, we're going to actually concentrate on those switches that you'll see. So on the top, you have your drive disconnect switches, and then also the standby power is off. That should be illuminated all the time. Now, this is a way to turn the standby power on or off as needed. And now standby power is kind of like a last ditch effort. If something goes wrong or whatever, you can turn standby power on, and it should always be set to auto, so it should automatically kick on. If the plane senses that, hey, look, a battery has failed or an IDG has failed or something like that, The standby power has a sensing circuit that will say like, "Hey, look, power is dropping off. We're going to turn this on." And we won't get into a whole lot of the architecture of the standby power system here. It's just like kind of outside of our scope. But just know that there is a secondary system that's there to be redundant to turn up to return power or return power to the system as needed. The panel right below it, you'll notice that switch where it says like ground power on or off, and there's a little blue light that'll say ground power is available above it. Now that is the light that I was talking about earlier. That like if you plug up power to the P19 and everything is working well, that light will come on, and then you can turn ground power on by simply just flipping it up, and that will basically serve as like your infinite battery that's off to the side. The switches below that, you have a bus transfer relay that's down below. Now that bus transfer switch needs to always be an auto unless there's something that needs to get troubleshot. If you turn it off, it isolates the left and right sides and prevents the bus transfer. So if you're trying to isolate a problem, that's a very useful switch. And then if the maintenance manual calls for it, sometimes you'll end up flipping that switch too for various reasons. But generally speaking, it always needs to be in the auto mode, so that way your BPCU can do its job. If not, you're basically taking that box out and you're making these two systems exist simultaneously side by side, but like not connected to one another. So down below you have like APU generator, then you have like your different generator status and your transfer buses, and you can turn them on or off as needed. And that's really kind of it for that panel. Now, this may look like a big mess to you, but it's actually really not that bad. It's actually fairly simple once you kind of understand what's going on. It's even borderline beautiful when you start to think about the level of redundancy that has been built into this system, and all using one diode and a couple of relays and a bunch of switches. So if we're going to start at the top and just kind of like start from there, so your external power is going to connect to one of these two, right or left transfer buses. So bus one or bus two. All right. Now those transfer buses exist as kind of a connecting bit from the external power to the rest of the plane, but also from an IDG to the rest of the plane, or one of the bus tiebreakers, BTB, they're 1 and 2. That's those bus tie breakers. So those are breakers that open or close if they want to connect the two buses together. So if you have like an IDG failure on bus tie breaker 1, those bus tie breakers could be closed, so that way power could flow from IDG 2 over to the transfer bus number 1. Notice that the APU is also tied into that. So you have a APB breaker. So the APU tie breaker will close and then go into BTB1, BTB2, and then off to your bus transfer units. That EPC is the external power connector. Like it's another breaker that like can be once there's power available, you can flip a switch and then it closes that breaker, and it supplies power to the rest of it. And then from there, you're just simply flipping switches. Anytime you see one of those switches that's in the cockpit, the breakers are the ones that are going to be in like the cabinets below and in the E&E bay. And so so let's look at the green while we're looking at this. GCU is a generator control unit, so you have GCU1, GCU2. You have AGCU, that's the APU's generator control unit. SCU, I forget what SCU stands for off the top of my head. I don't see it defined here. It's another control unit of a different type. BPCU, that's the bus tiebreaker control unit. It stands for bus power control unit, and so that basically like does the thinking to say like where's power coming from and where is it going, and that's that whole breaker system as you go. Now, if you look, you have main bus 1, main bus 2. It comes off of the transfer bus 1 and transfer bus 2, and you have power that can go to the galley on either one, and then you have service buses that are your AC ground service bus 1 and bus 2 that goes to your two different batteries. You always have a a primary battery, then an auxiliary battery, or bat one, bat two, depending on who you talk to and like what their backgrounds be and what they refer to it as. Then you have your TRU 1 and 2. That will go that way. And so anything that's red is DC, anything blue is AC. So TRU takes your AC power and converts to DC power and sends it all out, or vice versa, depending on how you arrange it. Then you have your 28 volt DC bus, 28 volt DC battery bus, which is different because that means it's directly tied to the battery, as opposed to getting DC power from somewhere else. 28 volt DC bus 2, the hot battery bus. Now let's talk about what a hot battery bus is. A bus is nothing more than you think about, like you're busing electrons around. It's a connector between point A and point B. So in this case, for a hot battery bus, it is a battery connector. So that hot bus, hot meaning that it's always on, and so unless you physically go and turn it off yourself. So like your hot battery buses are really important for emergency situations. That means that like if something were to happen, that hot bus is physically tied to the battery, and so you know that you have at least that amount of time, or however long your battery's going to last. You have that available to you. You have a 28 volt DC switched hot battery bus. So you can turn that hot battery bus on and off in that particular situation and what that ties to. You have your static inverter, and then you have your AC standby bus. So if the AC standby gets kicked on, it can go into the static inverter, and then that will invert electricity and then supply it to the DC system, charge the battery, all that good stuff. So that's kind of like the 737 Max's hierarchy of how power flows around. It really is something to see once you see how well thought out it is, and how intricate it actually is, and then how simple it is. It doesn't take a whole lot of like super duper computers or anything like that. Even though all those GCUs are computers, you don't necessarily need them to make the aircraft work. It's taking DC power, AC power, and turning it, inverting it, transforming it as needed. So that way, any one power source should be able to power the whole plane, which is pretty cool. All right, so this is what the Ford electronic equipment and compartment components look like. So you'll hear me especially say eBay. That's what we're talking about, the E and eBay, electronic and equipment, bay or unit or area. So the eBay is broken down into different racks. So the E2, E3, E4 racks. So think about E2 being the top, and then going down, if I remember correctly. And you have the the P91, P92 panel, the PDP1, PDP2 panels. Those are power distribution panels. That is fundamentally like what we're talking about here. Batteries are going to be in the bottom center that are there. There's typically two batteries that are there. But though you can have a one battery system depending on the configuration the airplane was built in for the carrier. And then throughout the rest of this, you can see all of the different components that we have talked about, and where they're at on the rack of a standard 737 Max. So top left, you have the transformer rectifier 3 and 2, the bus power control unit, the BPCU, GCU2. So that's going to be if you notice that like that GCU will control that side of the airplane's generator. Then you have over on the far right, the APU start converter unit. It's a power distribution piece for the APU system. AGCU up at the very top. It's the aviation or the APU generator control unit, and the GCU1 for the other generator. Then you have TRU1. So notice that TRU1 is on a different rack in a different place than TRU2 and 3, and that's a redundancy thing. You have the main battery charger, despite the fact that it's like way far away from the battery. That's where the main battery charger is. I'll tell you that is a bear to get in and out if you have to take it in and out. The static inverter is right below that. We've already talked about PDP1 or P91. You have the J9 box. So the J9 box has a bunch of relays and random things that are in there that kind of tie into the power distribution unit. And then you have the auxiliary battery charger right there in the center. Notice that DPC 1 and 2 is at the very top center rack. That's your digital processing display units. I might have got that acronym incorrect, but like the DPC1, DPC2 are right there, and all the other RNAV boxes are all put in there for you to see. But that's what the eBay looks like, and that's something that you'll end up becoming intimately familiar with, because regardless of what you do on the aircraft, unless you're doing strictly only sheet metal, this is the nerve center. This is like the heart of the airplane. Is actually right here, and so you need to get comfortable operating with it, and remembering where everything's at, so that way you can show up at a gate one day and be able to troubleshoot.